Welcome everybody to our next video in our series on probability and statistics. I am Dr. Lathram, and today we will be talking about the student T family of distributions and estimations of Gaussians. So let's begin our discussion of the student T distribution by recalling some theorems that we proved a few videos ago, but now we're actually going to put to some work. So the first one is we are supposing that we have an independent, identically distributed random sample, y1 up to y sub n, and these are normally distributed with a mean of mu and variance sigma squared. Then the important fact that we need is that the sample mean y bar and the sample variance s squared are going to be independent. Now the second theorem that we have, also we begin with a collection of independent, identically distributed random variables, y sub 1 up to y sub n, each one distributed normally with a mean of mu and variance sigma squared. Then we know that y bar is actually distributed normally with the same mean, so the mean of mu, but now the variance gets scaled by a factor of 1 over n. So that y bar is distributed normally with mu and sigma squared over n. And finally, the last theorem that we will make use of is if we have y sub 1, y sub 2, all the way up to y sub n, or one more time, an independent, identically distributed random sample of normal variables with a mean of mu and a variance sigma squared, then n minus 1 times the sample variance divided by sigma squared is actually distributed as a chi-squared distribution with n minus 1 degrees of freedom. And so now for a definition that may seem a little bit just out of left field, and why would anybody want to come up with this particular kind of definition? Well, you'll really see in just a little bit that there really is a method to our madness, that we are actually heading in a good direction. And so here we go. If we've got x and y are independent random variables, so x is distributed standard normal, and y is distributed as a chi-squared distribution with new degrees of freedom, then we're going to define a new random variable t, and t will be x divided by the square root of y over nu. Then this random variable t is said to have a student t distribution with new degrees of freedom. And of course we'll denote that with a capital T tilde t with a little nu indicating the number of degrees of freedom. Now the corollary to those three previous theorems that we had talked about is evident now. So if we have y sub 1, y sub 2, all the way up to y sub n, and they are independent, identically distributed random variables distributed normally with a mean of mu and a variance sigma squared, then our variable t, which is defined as y bar minus mu over s over root n, is distributed with a t distribution with n minus 1 degrees of freedom. Alright, so let's see exactly how this comes about. So we know that y sub k is normally distributed with a mean of mu and a variance sigma squared, for k being 1 up to n. And so we know that y bar is going to be distributed normally with a mean of mu and a variance sigma squared over n. Now, if we subtract the mean, divide by the variance, or divide by the standard deviation rather, then we get something that's normally distributed with a mean of 0 and a variance of 1. So we get something that's distributed standard normal. Now, we also know that s squared is independent the sample variance is independent of the sample mean, and so n minus 1 times the sample variance over sigma squared is distributed as a chi-squared distribution with n minus 1 degrees of freedom. And so if we write out what our variable t is now, then we've got our y bar minus mu over sigma over root n, that divided by the square root of n minus 1 times the sample variance over sigma squared, that divided by n minus 1. So all of this is underneath the radical. Well, we can cancel our n minus 1s. We take the square root of the sample variance, and so we get s over sigma. Our sigmas cancel. We have an s over root n, and so we end up with this expression y bar minus mu over s over root n, and that is distributed with a student t distribution with n minus 1 degrees of freedom. And so now kind of a natural question is, well, what does the CDF or the PDF of the student t distributions actually look like? Well, it's kind of an interesting way of deriving that. And so let's take a look and see how that happens. Now we have x and y are independent. Now the joint probability distribution, because they are independent, is going to be a product of the marginals. And so that tells us that f of xy is going to have this kind of an expression here. We can put the exponentials together. And so this is actually going to be defined since x is going to take on any value because it's normally distributed. So we have minus infinity to infinity. Now y can only take on values from 0 to infinity. And so our joint probability distribution is actually defined on the upper half plane from minus infinity to infinity cross 0 up to infinity. So we've got the upper half plane here. And so now let's consider a transformation. And that transformation will let x and y's go to t and w, where we define t as being x divided by the square root of y over nu, and w as just being y. And so if we look at the Jacobian of that transformation, then we end up with a matrix that looks something like this. We take the determinant, and we see that we have a Jacobian of root w over nu. And so now kind of the important part of this transformation is this y plus x squared. Well, y plus x squared is going to be w plus t over root w squared. And so if we factor out a w out of that, then we have an expression of the form w times 1 plus t squared over nu. And so the whole purpose for this, the joint PDF of t and w, is going to have this form to it. Now that kind of looks a little bit messy, but the really important observation is that this distribution actually looks like a member of the gamma family. It's a member of the gamma family with t actually being listed here as kind of a parameter of our family. And so what this means is that w is actually distributed as a member of the gamma family with alpha is equal to nu plus 1 over 2 and beta being 2 over 1 plus t squared over nu. And so what happens, we are able to find the marginal distribution for t really just by integrating with respect to w. And so if we do that, we see that our integral with respect to w is just going to be a gamma function times its scaling constants. And so we end up with a PDF for our student t distribution that has this form here. Kind of one interesting thing about that is if we take nu to be 1, so if we have 1 degree of freedom, then the cumulative distribution function is just the arctangent function. And so now let's talk a little bit about some philosophy of statistics. So this really isn't something that's essential and necessary for doing the math, but it is something that does kind of help guide our thinking about what we are doing. And so kind of one way of thinking about this is that you have this, so you have truth and reality kind of back here in the background. So this is actually what exists. There is something true back there. And what we are doing as statisticians, so the truth is in the background, and what we are doing as statisticians, we are doing experiments. So we're doing experiments, we're gathering data, and somehow we want that data or we want to use that data to then gain information about the truth that's in the background. So that's really what we're doing with our experiments. Now later on we're talking about hypothesis testing and those kind of things. We've got two other kind of layers in here. We've got a null hypothesis layer, and then we've got an alternative hypothesis layer in addition to the truth layer that's really going on back here in the background. But we'll get to that in some later videos. So here's the game that we have going on. The truth in the background is that we have a normal distribution with a mean of mu and a variance of sigma squared. Now what we are doing, we are taking n random samples, so n independent identically distributed random samples, y1 up to yn, from the truth that's actually going on. Now we don't know. So here's the game. Situations or games that we can play, we want to know the mean, but we don't know the standard deviation known. So suppose we know that much. We can also play the game where we want mu, but the standard deviation is unknown. And then finally, we can say, well, I'm not really concerned about the mean. I want to know what's the standard deviation. So those are kind of the three things that we can talk about. And we've already done the work now to solve those problems or to have solutions to this particular game. So what are the solutions? So for the first question, if we want mu, but we know what the standard deviation is, then we've got our z variable. And our z variable is just y bar minus mu over sigma over root n. And we know that this is going to be distributed with standard normally. Okay. For the second problem, we want mu, but we don't know the standard deviation, and for that we have the distribution that we just used. So our t variable, we have y bar minus mu over the sample variance divided by root n, and that's going to be having a t distribution with n minus 1 degrees of freedom. And finally, if we want to know sigma, then we have n minus 1 times the sample variance divided by sigma squared has a chi-squared distribution with n minus 1 degrees of freedom. And so that will give us the answer to the third question. Now, what those are all examples of something called a pivotal quantity. So a pivotal quantity is an expression that has the following characteristics. First of all, it's a function of the sample measurements and the unknown parameter, say theta, where theta is the parameter that we want to know. And it has a probability distribution that doesn't depend on the parameter theta. So if you think back to the solutions that we just had, the z variable was distributed standard normally, no dependence on mu. The t variable had a t distribution with n minus 1 degrees of freedom. Again, no dependence on mu. And for the sample variance, we had a chi-squared distribution with n minus 1 degrees of freedom. And so that also had no dependence on sigma at all for the particular distribution. So those were examples of pivotal quantities. And so one thing that you can do with those pivotal quantities is something called finding a confidence interval. So what we've got two estimators, theta hat sub L and theta hat sub U, are upper and lower bounds respectively for the parameter that we want to find, theta, with a confidence coefficient of 1 minus alpha. So alpha is going to be a number, usually in this kind of situation we say that alpha is going to be a very small number, so something like 0.05 or 0.01 or something like that. So we want to be highly confident, so we want our confidence coefficient of 90%, 95%, 99%, if and only if. So the probability that our parameter that we're interested in is going to be in between our lower bound of theta hat sub L and our upper bound theta hat sub U, and we want that to have a probability of 1 minus alpha. And in that case, we say that the interval theta hat sub L to theta hat sub U is a two-sided confidence interval. Now, we can also have one-sided confidence interval. So if we just had an upper bound for theta with a probability of 1 minus alpha, or we can have a lower bound for theta, again having a probability of 1 minus alpha. So we can have one-sided confidence intervals as well. So there's nothing really prohibiting that in this respect. So now let's do an example of a confidence interval for mu where sigma is not known. And so, again, the background. So the truth is that we have a normal distribution with parameters mu and sigma squared. We don't know mu, and we don't know sigma squared. So we're going to take 25 samples from this. So we've got 25 independent, identically distributed random variables. So from this truth distribution that we have. And then, since we don't know sigma, we will go to the t family. So we have our random variable t being y bar minus mu over the sample standard deviation, so the square root of the sample variance over 5. Where does the 5 come from? The square root of 25. And we know that's going to be distributed with a t distribution with actually 24 degrees of freedom. Now, we wish to have a two-sided confidence interval, say of 95%, and so the t distribution is going to have be a PDF that looks something like this, and so we're going to have half of the area that we're willing to be wrong in, so half of the area above our interval and half the area below our interval. Now, there's nothing really that says it has to be half and half. If you want to have a little bit more on the top and a little bit less on the bottom, that's fine. You can do that. You have that ability, but typically when we say our two-sided confidence intervals, you're assuming that that's probably going to be a symmetric two-sided interval, but there's absolutely nothing that says that it has to be that way. And so what we need to find two values, a lower bound and upper bound. So our lower bound, now this is a little bit about the notation. We usually denote that as t sub, and then the subscript is actually going to be the percentile that we have for that value. So we want 2.5% below, so we get t sub 0.025. We want 2.5% above, so that puts us at t sub 0.975. And so we need these upper and lower values so that the probability is going to be 0.95. Well, R will let us figure that out very, very easily. So if we want the t of 0.025, we go to the go over to R. We've got this command qt that will give us these things for 24 degrees of freedom, and same thing, similar command to get the upper bound, and so we've got values of 2.063899 for our estimates for our upper bound and lower bound. And so the rest of it, this is just giving us 0.95. We set our upper bound and our lower bound, and then we solve for mu. So solving for mu, we get this expression, and so our 95% confidence interval will be, so from our sample, we take the mean, subtract 0.41 times the sample variance, and add on that value times the sample variance to the mean, and that gives us our confidence interval. So a second thing that can happen in these situations is we're doing this experiment and we ask the question, well, how much data do we need? So the setup is we're supposing that we would like our error of our mean in our data, mu, to have some fixed value, say epsilon, but we still want to have a confidence coefficient of 1 minus alpha. So what do we do with that? Well, we still know that y bar minus mu over sigma over root n is distributed standard normally. And so for a two-sided confidence interval, we want the probability that the absolute value is going to be less than z of 1 minus alpha over 2. So again, we're putting half of the area above, half of the area below, and we want that to have a probability of 1 minus alpha. Well, solving for those values, we want our error to be less than epsilon, and so sigma over root n is equal to our z of 1 minus alpha over 2. And so in doing that, we can solve for n. So we get n being an expression that looks like this. Now, knowing sigma, we are able to actually calculate that value of n. That's going to meet our desired conditions. So the question is really, well, what happens if we don't know sigma? So if we don't know sigma, then somehow we have to have some other information to be able to say sigma is going to have this value. So what if we don't know sigma? And we need some other information to figure out, to say this is what sigma is going to be. So for example, we can have our truth is that the training times for a particular method are normally distributed with a mean of mu and a variance of sigma squared. So that what the trainer wants to do is to estimate mu within 1 minute with a 95% accuracy. The question is, how many workers must be included in the training group? So we want mu, we don't know what sigma is. And so problems will then have to give you more information, such as the trainer estimates that the range of times is going to be about 12 minutes. And that gives us the extra information that we need in order to estimate sigma. So how do we do that? Well, since the range is going to be in a 12-minute interval, then pretty much we know that all of the data, for all intents and purposes, all of the data is going to be captured within, say, 4 standard deviations. So here's where we're kind of doing our estimate. We're assuming in that 4 standard deviations. So if we say 4 standard deviations, is going to be our range of 12 minutes, then that's going to give us a value of sigma for about 3 minutes. And so here we've got this extra information. So the information from an expert who knows what these things should be, and from that information we are able to say that, okay, our standard deviation is going to be this. So alternatively, we could say that sigma is going to be this value from a previous experiment, so something that somebody else has done. If we try to do our own experiment with this, we can try doing 2 experiments. So the first, we want to know sigma, so maybe we can use, in the first experiment, we'll have a sample size of m, random variables. So we know that m minus 1 times the sample variance over sigma squared has a chi-square distribution with m minus 1 degrees of freedom. And so taking our confidence coefficient for the first experiment to be 1 minus beta, we have this interval. So we have half the area below, half the area above, and then this is going to give us an interval. If we solve for sigma squared, then we have a lower bound of sigma prime, which is going to be this expression, and then we've got an upper bound of sigma double prime, which is this expression. So now with if we want our error between our value that we're estimating and our mean to be less than epsilon, then we have this expression that we know that the variance, our standard deviation, so our actual truthful standard deviation, is going to be smaller than sigma, going to be smaller than sigma prime, or 1 over sigma is going to be smaller than 1 over sigma prime. Our error is going to be less than our required error bound for epsilon, and then we have our root n. And so taking that equal to z sub 1 minus alpha over 2. So now this is preparing for our second experiment. So our second experiment, we have y bar minus mu over sigma over root n, distributed standard normal, so we're using our z values. Taking our estimate of sigma prime, in this case, we are able to solve for n. So our sigma prime comes from our previous experiment, and so we get a value for n of this expression. Okay, so this expression is involving our lower bound for sigma. So now let's see what happens. So back in our previous calculation, if we do our probability, so that y bar minus mu over root n over sigma is going to be smaller than z of 1 minus alpha over 2, then kind of multiplying both sides by sigma, dividing by root n, we end up with this expression. Now, y bar minus mu, the absolute value of y bar minus mu, we want that. So if we kind of plug in the values that we know now, our upper estimate for sigma is going to be sigma double prime. So we have this expression, and so if we substitute in the expression that we had for n, then we get this extra factor showing up that we end up with our error is not going to be less than epsilon anymore. Our error is going to be less than epsilon times the ratio of sigma double prime over sigma prime. So the ratio of our estimates, our upper bound over our lower bound for sigma. And so if we knew actually the true value of sigma, then this becomes 1 and everything is great and wonderful. So if we have to estimate it on those lower bounds, then in truth, our value, our probability is not really going to be maybe our desired error that we want, but it's going to be our desired error scaled up by this ratio of our upper bound over lower bound for our variances. And so you can play games in this situation. You can pick your sample size of your first experiment so that this ratio is really, really close to 1 so that you're getting pretty much the area that you want. You can play those kinds of games, but if we're trying to estimate our sample size without really knowing what sigma is, then it's somewhat of a difficult process, and we can't really necessarily get it without assuming information kind of outside what our assumptions are. And so in the end, you're kind of forced to have some other outside information in your problem in which you can say, yes, your variance, your standard deviation is going to take on this particular value. And so now let's do an example with exponential functions and pivotal quantities. So the setup is that we've got an y that's distributed exponentially with parameter theta. Theta we don't know. Then our expression u equal to y over theta, we say that that's going to be a pivotal quantity. Let's see if we can actually prove that. So if we look at the transformation for u being y over theta, so that y is going to be theta times u, then for the distribution of u, we have our expression that's going to be f sub u is going to be f of theta times u times dy du. Well, that just gives us e to the negative u, because we assume that y had an exponential distribution with parameter theta. And so what we have now, this is also an exponential distribution with a parameter value, with a fixed parameter of 1. And so it's not dependent on theta anymore. And that's exactly what we needed for this particular situation. So we've got an expression, we've got a pivotal quantity, y over theta, that has a distribution that doesn't depend on the parameter theta. So if we want a two-sided 95% confidence interval for a and b, so we need to find values a and b, a being the lower bound, b being the upper bound. So the probability of u being in that interval is 0.95. So what do? We have half the error above, half the error below. So going over to R, we can find the upper bound with the QEXP function. We can find the lower bound also with the QEXP function. And so if we then do some algebra on there, flip both sides, change the direction of the inequality, then we get an interval for whatever our y value is over b, for our lower bound, y value from our experiment over a for our upper bound, and we've got a 95% confidence that our parameter theta is going to be in those particular values. So now let's see that this actually really does work when we fire this up and experiment in R. So let's get R started. And from our experiment, we know that, we had our truth value. So let's say that we have our truth value. Let's pick a value for theta being, I don't know, how about 12.8. So you pick a value for theta being 12.8. Then we need upper bounds and lower bounds. So again, let's pick a value for alpha. We'll say alpha is going to be 0.95, or so we want alpha to be 0.05, so that our confidence is going to be 95%. So 95% is going to be our confidence coefficient. We need a random sample. So let's take a random sample, say y, from our truth distribution. So random sample of from our exponential distribution with parameter theta. So we want to take a random sample of one value with a parameter of 1 over theta. And so we get a y value of 4.517088. Okay, so that's our sample value. So we want to be able to estimate our confidence interval from that. So remember that for the lower bound on our confidence interval, we needed we want half our area below, so QEXP, so that's distributed with a parameter value of 1, and so we want our half of our area, so alpha over 2 with parameter 1, and so we get a lower bound of 0.0253171. For our upper bound, we have B being QEXP alpha over 2, but since it's an upper bound, we want our lower tail to be false. And so we've got an upper bound of 3.688879. Okay. So now, what are our confidence values? Well, for our lower bound on our confidence interval, that was y over b. So we've got 1.224515. For our upper bound, we've got y over a, which was 178.4154. So that's a pretty big interval. But still, what we found in that situation is that is our true value in that interval. So we've got y over b. Is that less than our value theta? And is theta going to be less than y over a? Sure enough, that is true. So kind of an interesting part of this is now, okay, so it worked this time. Where does the 95% actually come into play? Well, let's test that. Okay, so let's say that if we had maybe 100 researchers and we wanted each one of these 100 researchers to do this experiment. So let's say that we've got 100 researchers, so we'll say we've got a vector that's of zeros that's 100 long, and so what we want to do now is let's do a loop for I in 1 through 100. Now what we want to do is we want to perform this experiment. So we have A, we have B, that's not really dependent on our experiment, but we do have our random sample Y. And so y is going to be a random sample from our exponential distribution. We're taking one sample with parameter 1 over theta. And now we want to see if this is actually right. And so for our ith value, we will let that be. Is this a true statement? So is y over b less than theta, and theta less than y over a, is that going to be a true statement? So let's see what happens when we just run that loop. Then we get x's being these values, so 1s and 0s. So let's see how many 1s and how many 0s that we have. So some x, sure enough, we were right 95 times out of 100. Which means that really for that we were wrong 5 out of 100. So if we really do this, so where does the 1 minus alpha come in? It means that, so it's kind of a guarantee that yes, we perform this experiment, we will be right 95% of the time, but it also means that on average we will be wrong 5% of the time. And so when we're performing these experiments, we never really maybe know, are we going to be wrong? Or when we're going to be wrong. So every time that we perform the experiment, we have to remember that possibility, that it's not just a possibility that we will be wrong, but sometimes we will, absolutely positively, we will be wrong 5% of the time. So it's not one of these things that maybe will be wrong. No, we are guaranteed, on average, 5% of the time, we will be wrong. And so that's kind of one of these things that when we are doing our hypothesis testing, you probably maybe have heard that we can't say that the null hypothesis is true. All we can say is that we failed to reject the null hypothesis. This is really the reason, because it's not just a possibility that we are going to be wrong. Statistically, we will be, beyond a shadow of doubt, we will be wrong 5% of the time as we're doing these samples. Otherwise, the tails of the distributions would not be what the tails of the distributions are. So I hope you've enjoyed this video, and I look forward to seeing you all next time.